All right, so what we're talking about today is we're going to be talking about what's called the first derivative test, okay? And we use it to tell where a function is increasing and also where it's decreasing. Now, it's a tool, okay? And what I want to look at today is I want to look at this, okay? So right here, if you take a look at this function is decreasing, all right? And if you look, all of the derivatives, every x value here, okay, the tangent slopes will all be negative except for right here, because at right there we have a horizontal tangent, okay? So right there at x equals 3 or f prime of 3, we should know that that's going to equal 0, okay? And then looking at this, we can tell on this side of x equals 3, okay, the function is decreasing, right? It's going down. And even at 3, we say it's decreasing, okay? And I'll explain that in just a minute, okay? So right here, if we look at this, all the tangent slopes would have to be negative. So that means f prime of x for all of these x values, they would have to be less than 0. The derivative would have to be negative, okay? Now the derivative is not negative at 3, okay? But it is decreasing all the way until 3. And then right here, all of these after 3, okay, all the tangent slopes are positive, okay? So what that means is that f prime of x would have to be greater than 0, okay, for this side, okay? Now, looking over here, okay, all the points right here at x equals 3 again, okay, we can tell right there that f prime of 3 would have to equal 0. There's a horizontal tangent right there, okay? So f prime of 3 would equal 0. Over here, all of these, okay, all of these points on the curve, okay, the derivative or the tangent lines would all be positive, which would make the derivatives all be positive, okay? So on this side, f prime of x is greater than 0. How about over here? Well, also over here, the tangent lines are all positive, right? So right here, f prime of x would also have to be greater than 0. Okay, so now I'm going to talk about some definitions now, and then we'll come back and I'll tell you how do we state where this is increasing. And it's not necessarily, okay, if the derivative is negative, then it's decreasing. That's not necessarily true, okay? And where the derivative is positive, it's increasing, all right? Okay, so we'll talk about that in just a second. Let me slide this up. So what is the strict definition for increasing, okay? So function f is increasing on an interval if for 2 points, x1 and x sub 2, in the interval, and x sub 1 has to be less than x sub 2. Now that would mean that x sub 1 is to the left of x sub 2 because x sub 1 is smaller than x sub 2. So this one's on the left, this one's on the right, okay? Then that would imply, if it's increasing, that f of x sub 1, the one on the left is going to be smaller, okay? The y is going to be smaller than the one on the right, okay? Because if x1 is less than x sub 2, this would be the one on the left, and we're saying it's smaller than the one on the right for it to be increasing, okay? So think about it like this. Here's a point, right? That's x sub 1, and here's a point x sub 2. This would be increasing if this one is lower than this one, okay? And it would be true if for any two numbers in that interval, this were to be true. The one on the right is higher, okay? A function f is decreasing on an interval if for two numbers, x1 and x sub 2 in the interval, x sub 1 is less than x sub 2. So the x sub 1 is the one on the left, x sub 2 is the one on the right, okay? That would imply that f of x sub 1 is greater than f of x sub 2. Now that means that the one on the left is higher, so it would look something like that, okay? And this would be the one on the left, okay? And the one on the left would have to be larger than the one on the right, okay? Now, that's the strict definition of how we can tell increasing and decreasing, okay? All right, so back up to here, any 2 points, even including this 3 right here, okay, this one is going to be lower than all the other ones. So the one on the right is always any 2 points on here, including at x equals 3, we would have to be decreasing here, okay? And over here, we'd have to be increasing. If we take at x equals 3, at any point after that, the one on the right is going to be larger, okay? So this is increasing, okay, for 3 with a bracket to infinity, okay? And that's by the definition of increasing. All right. Now, where is it decreasing? Well, it's decreasing all right in here, including at 3, okay? Because at 3, all right, that point right there is going to be lower than any point on the to the left of it, okay? So it's decreasing for negative infinity up to 3, including. And we're including 3 on both. That's where it's switching, okay? And this is by definition. Okay? Now, this is the one that we used calculus way too much to determine this, all right? And so we think calculus is the end-all be-all, and we can just use calculus, right? And you have to think about this, okay? Where is this increasing? What does it mean to be increasing? That any point on the left is lower than any point on the right. Well, that's true up to this point, right? Any point to the left of this is going to be lower than that one, okay? And any point to the right is going to be larger than this one. So what that means is this thing is increasing the entire time. So it's not necessarily, I'm emphasizing this on purpose. I don't want you to think that the derivatives can directly tell you where it's going to be increasing and where it's going to be decreasing. Because if we have a derivative of 0, it could still be increasing right there. It's increasing on an interval, not at a point, okay? So this would be increasing, okay? And we would say on, I should have said on over here too, increasing on an interval. So it's increasing on the interval, negative infinity to positive infinity, okay? All right, so now let's take a look. How can we use calculus to help determine where it's increasing and decreasing, okay? And so this is, we can use derivatives, okay? But we can't look at just derivatives alone, okay? So let f of x be a continuous on the closed interval a to b. So it has to, this is the test for increasing, okay? This is what we're gonna use to determine it, okay? And differentiable on the open interval. This is a stipulation on a lot of theorems and tests, okay? It has to be continuous on the closed and differentiable on the open, okay? If f prime of x is greater than 0 for all x in the open interval a to b, then f of x is increasing. Now notice, the derivative has to be positive on the open one, right? And then we would say it's increasing on the closed one, all right? So this is where we pick up, like up here, this is how we pick up the 3, okay? So the derivative is positive, not including 3 on, right? So f prime of x is greater than 0, right? From 3, not including 3, to infinity. But we would say it's increasing starting at 3 and going on, okay, to infinity. So we would say f prime of x is greater than 0 on the interval 3 to infinity, but then we say it's increasing on 3 to infinity, and so we're going to include that point 3, okay? Now this isn't necessarily true if it's not continuous and differentiable, okay? All right? And then if the derivative is negative for all x in a to b, then f of x is decreasing on the closed. So the derivative is negative all the way from negative infinity up to 3, but not including 3, but then we would say it's decreasing, okay? All right. So over here, okay, this is the one that messes people up because people say this, oh, it's only increasing from negative infinity to 3 and then union 3 to infinity, right? We're strictly using positive derivative to mean increasing. That's not true, okay? It's not true, all right? So we would say if I ask you, okay, where is the derivative positive? Where is it greater than 0? You would answer that with this. It would be negative infinity up to 3, not including 3, union, comma, or not comma, 3 to infinity, all right? So the derivative being positive helps us to determine increasing, but it doesn't strictly tell you where it's increasing, because if we use this definition of increasing, we would actually say it would be increasing on negative infinity to 3, including 3, union, including 3 to infinity. And this is ridiculous saying it like this, because here we're including 3 and here we're including 3. We only need to break it up when we're not including it, right? But we are including it, okay? So this is not a good way of writing this. We would just say negative infinity to positive infinity. Any 2 points on here, the one on the left is going to be smaller than the one on the right, okay? And this isn't going to come up much, okay? But if f prime of x is equal to 0 for all x in an interval a to b, then we say f of x is constant, okay? So it's not increasing, it's not decreasing, it's just staying the same value, okay? It's just staying constant. All right, let's talk about the first derivative test now. So this is the first derivative test, and it's a test. We have a test for absolute extrema. That's the closed interval test, okay? But this is a test to determine if we have relative extrema or relative max and relative min, okay? So if f prime of x changes from negative to positive, okay? So that means decreasing to increasing. So it's going down and then back up at x equals c. Then we say f of c is a relative minimum, because for this, it changes from being negative, okay? And remember, negative derivatives tell us it's decreasing and positive derivatives tell us it's increasing. So it's doing this, it's coming down and then back up. It's changing from decreasing to increasing. That means we'd have a relative min. If f prime changes from positive to negative at x equals c, then f of c is a relative maximum. So if it's changing from being positive to negative, that would mean it's changing from going up to going down, and so that's where we have a relative maximum. Okay, so the way we're going to find relative extrema, okay, we're going to do the same thing we've been doing: locate critical numbers, okay, and then we got to make sure that the critical number is in the domain of f of x. So we got to write the domain of these functions first, okay? Then we need to solve f prime of x is equal to 0. We also need to solve where f prime of x is undefined. And then we're going to make a sign chart and determine the signs of f prime of x in each of the intervals, okay? So that's what we're going to do. So we want to find the critical numbers, the open intervals on which the function is increasing and decreasing, and then locate any relative extrema, okay? So we have f of x is equal to x cubed minus 3/2 x squared, okay? That's a polynomial. And what do we know about polynomials? The domain is negative infinity to positive infinity. So right off the get-go, we want to state the domain. So the domain is negative infinity to positive infinity. Okay. Next, we want to start finding the critical numbers. Okay. So to find the critical numbers, we need to find the derivative. Okay. So f prime of x would equal 3x squared minus 3/2 times 2x. Okay. And we're going to clean this up a little bit. This becomes f prime of x is equal to 3x squared minus 3x. Okay, so the next step in this is we want to find where does f prime of x equal 0, and we also want to figure out where does f prime of x, where is it undefined? Okay, so f prime of x, we'd set this equal to 0. So 3x squared minus 3x is equal to 0. There's a GCF here of 3x. So we can rewrite this as 3x times x minus 1 equals 0. Well, this is going to happen when x equals 0 and when x equals 1. So there's two critical numbers, and they're in the domain, so they are critical numbers, okay? Where is f prime of x undefined? Well, in this case, since this is a polynomial, polynomials are always defined. So this is never, it's never going to be not defined. The first derivative, that's a parabola, right? Because we have the highest power is 2, okay? All right, so we're going to use the domain, and we're going to use these critical numbers to make what's called a sign chart. All right, and we actually did sign charts last year in Honors Math 3 because we used it to determine the polynomial inequalities. Okay, so I'm going to label this intervals. Okay, and using the domain in our critical numbers, the smallest one is negative infinity. So we're going to start our intervals at negative infinity up to our first critical value, which in this case would be 0. So comma 0. And then we're going to start up at 0. So we're throwing out from negative infinity to infinity, we're going to throw out the 0, and we're also going to throw out the 1 here, okay? So we're going to go from 0 to 1. And we don't want to include the critical numbers, basically, okay? And then we want to do 1 to, what's the next? Well, there's no more critical numbers, right? So we're just going to go to the end of the domain, which is infinity. Okay, so now we're going to test a point in each of these intervals. Okay, so a good point to check in this interval would be x equals -1. A nice point in this one would be something like x equals 0.5, and over here x equals 2. And then what we're going to look at is we're going to look at the sign of f prime. So that means we're going to put this x value into the simplest thing, and a lot of times I would say put it into the factored form, okay? Because if you put it into the factored form, it's going to be really easy to calculate what it is, okay? So if we put -1, okay, into the 3x, right? Because this is the factored form of 3x squared minus 3x. If we put it in here, that'd be 3 times -1. This would be negative, so our first factor is negative. And if we put -1 into the second factor, that'd be -1 minus 1. That would be negative. So what we have is a negative times a negative. So overall, that would be positive. Okay. And then at x equals 0.5, well, 3 times 0.5, that would come out to be a positive value. 0.5 minus 1, well, that would be a negative value. And a positive times a negative is going to give me a negative value. Okay. So this is telling me that all of the points in this interval, the derivative is going to be positive. And this one's telling me all the points in this interval, the derivative is going to be negative. And then for this one at x equals 2, well, 3 times 2, that would be positive. And 2 minus 1, that would be positive. And so we wind up with positive times positive, which is positive. Okay? And so the behavior of f is, okay, this is telling me that the function is increasing. Here, this is telling me the function is decreasing. Right here, because the derivative is positive, that tells me it's increasing. So the derivative changed from being positive to negative. So that means it changed from being going up to coming back down. We have a relative maximum right here, okay? And then we went from decreasing, so going down, to increasing, going back up. We have a relative minimum right here, okay? So now, I want to take out this, okay? I shouldn't have said this. Find the critical numbers and the intervals, okay? So a lot of times on the AP exam, they're gonna just say open intervals, okay? And then you don't have to worry about including the endpoint, okay? All right. So we would say from this sign chart, the analysis here, we could say that f of x is increasing on the interval negative infinity to 0, and we're going to include 0. And then union, and it's also increasing from 1 to infinity. And both 0, we can say that because both 0 and 1 are in the domain of this, okay? And then we could say f of x is decreasing on, and it'd be this interval right here, and it would be including 0 to 1, okay? All right, so pay attention even on the final, because the final is an AP exam. If it says open intervals, you just can get, well, it'll be multiple choice, okay? So if it's multiple choice, you're not gonna see brackets, you're just gonna see parentheses, okay? And if this was free response, we would accept it either with brackets or with parentheses, okay? All right, if it said open. All right, here we go. All right, we need to find f of 0 because that's going to be a maximum, okay? So f of 0 we need to find. Okay, so if we put 0 in here, well, that would just be 0, okay? And also f of 1. Okay, and f of 1, this would be 1, and then 1 minus, and this would be 1, so 1 minus 3 halves, or 2 halves minus 3 halves, which is negative 1 half. That's what we would get out of that, okay? All right, now you got to give a justification of why we're saying there's a relative max. You always have to do this, okay? If you don't say this, you might as well have not done the problem, okay? Because this is where you get the justification, okay? So we would say, we know that f of x, okay, there's a proper way of writing this up, and the College Board is looking for, when they grade your AP exam, they're looking for the specific language that you're going to use right now that I'm going to teach you, okay? So we would say f of x has a relative maximum, okay, of, and at x equals 0, this is 0. So we have a relative max. So we'd say f of x has a relative maximum of 0 at x equals 0 because, and how do we know that it's a relative maximum? It's because f prime of x changes from positive, so it changed from positive to negative at x equals 0. Okay, now I want to say this. You cannot give a justification of why is there a relative maximum at x equals 0, and you say because f is changing from increasing to decreasing. That's absolutely true. There is a relative maximum because of that, but here's the problem. That is not a calculus justification. That's an algebra justification, and you're taking calculus. So you have to give a calculus justification for it. And if you say, oh, it's because the f is changing from increasing to decreasing, you're not using any calculus to say that, okay? Now, to make that justification, okay, or to make that conclusion, all right? Yes, we use calculus to get the increasing and decreasing, but when you say strictly that it's changing from, the function is changing from increasing to decreasing, when you start to say it like that, you're not using calculus to justify whether there's a relative maximum, okay? All right, now we also have a relative minimum because it changed from going down to going up, right? And okay, so what is that? Is that the derivative was negative, the derivative changed from being negative to positive, okay? So we say f of x has a relative minimum of negative 1/2 at x equals 1 because f prime of x changes from negative to positive at x equals, and you got to throw in that at x equals 1 and up here at x equals 0. You have to add that, okay? All right, guys, so that's how we justify relative maxes and mins. We do the sign chart, okay? This is a fairly simple one, okay? Because the function to take the derivative was fairly simple. If they ask you to do this, this whole shebang like we did right here, then what happens is they usually give you a really simple function to do it with, okay? They don't want to bog you down with time, okay, with taking this long derivative. Or sometimes they'll give you the function and they'll give you the derivative, so you don't even have to worry about figuring out the derivative. You just have to do the analysis behind it, okay? All right, so we have a couple more examples to do like this, and then we'll be done. Okay, so let's do another one. So this is the same question. We find the critical numbers, find the intervals, okay? My notes that I don't have open, so I don't know what happened that switched to open, okay? On which the function is increasing, decreasing, and then locate any relative extrema, okay? So here's our problem. F of x is equal to 1/2 x minus cosine x, 0 less than x less than 2 pi. Okay, so this is our domain, right? So our domain is this. So we don't have to worry about any values outside of that, okay? So let's go ahead and take the derivative of this, okay? So that means f prime of x would equal, okay, so the derivative of 1/2 x would just be 1/2 minus, and then the derivative of cosine x is negative sine x. And so that means f prime of x is equal to 1/2 plus sine of x. Okay, so we want to figure out, okay, where is f prime of x equal to 0? And we want to figure that out. And we also want to figure out where is f prime of x undefined, right? Okay, because that's going to give us the critical values, okay? So that would make this one 1/2 plus sine x is equal to 0. This one is, it's never going to, because sine x is continuous, right? That's a continuous function. There's no place, I say continuous, but this is defined for all values of x. There's no breaks in the graph, right? So that means this is never going to happen. Okay, so then to solve this, I'm going to move my 1/2 over. So this makes sine of x equal to negative 1/2. Okay, so I'm going to draw a trig diagram for this. Okay, I know my sine of x is y over r, so I know my y is going to have to be negative because r is never negative. So that means down here, my y is negative 1 and my r is 2. Now this can also happen in this quadrant where y is negative 1 and r is 2. Okay, so when r is 2 and the leg is 1, okay, the other leg has to be the square root of 3. And this would have to be negative square root of 3. And that would make this reference angle in here pi over 6, because the angle that's always opposite 1 is pi over 6. And opposite 1 is this angle right here, pi over 6. So this angle x, okay, is equal to, all the way to here is 6 pi over 6. So that'd be 7 pi over 6. Okay, and then going all the way around, this would be 6 pi over 6. This would be 12 pi over 6 right here. Okay, and so that would be back off of pi over 6, and this would be 11 pi over 6. Okay, so now we're going to build, now we have our critical values. Both of those are between 0 and 2 pi. And now we're going to build our sign chart. Okay, so we have our intervals. And again, we use the domain along with these critical values or numbers to determine the breaks in these intervals. So we're going to start this with the smallest value in the domain, which is 0. And then we're going to go to the next, and then we're going to end it at 2 pi. So the left interval is always going to start at 0, and then you're going to go to your first critical number, okay? So in this case, that'd be 7 pi over 6. And then we're going to go 7 pi over 6 to the next critical value, which is 11 pi over 6. And then 11 pi over 6. And there's no more critical value, so then we're going to end it at the right endpoint of your domain, which it's not really an endpoint, but the end of it, which would be 2 pi. Okay, so now test points. Okay, so what's a good angle from 0 to 7 pi over 6? Well, 6 pi over 6 would be in here, right? So I would say x is equal to pi. Okay, from 7 pi over 6 to 11 pi over 6, I would say this one. I would say 3 pi over 2. Okay, so x is equal to 3 pi over 2. Okay, because that's in between 7 pi over 6 and 11 pi over 6. Okay, and then, okay, I would do something. Okay, we got to realize this one's the weird one. That's why I picked to do this problem. Okay, this one right here is really 12 pi over 6, right? 12 pi over 6 and 2 pi are the same thing. Okay, so I need to get a value between 11 pi over 6 and 12 pi over 6. So we could use something like this, 11.5 pi over 6, okay? Now, it's not good to have decimals, so if I doubled the top and the bottom, that would give me 23 pi over 12. 23 pi over 12 and 11.5 pi over 6 are the same, okay? Now, here's where we're going to go and we're going to use our graphing calculator to determine the sign of these, okay? Okay, so since this is a pretty easy function, okay, we're going to do, I'm just going to put it in. So actually, let's go to y equals. Let me clear this out, okay? Let me put in y equals. I'm going to zoom in a little bit so you can see the calculator a little bit easier, okay? So I'm going to put in our derivative, which is 1/2, and then plus sine x. Now we got to remember this is not the function. This is the derivative, okay? All right, so now I'm going to graph this from 0 to 2 pi. So I'm going to go to my window, go from 0 to 2 pi. And the highest sine goes is 1. So I'd go like from -2 to 2. And then we, you know what, I'm in degree mode. So press mode, make sure you're in radian mode. And then graph it. All right, and then what I'm gonna do is I'm gonna calculate, and we're gonna calculate values. Okay, so we're gonna put in pi. And what do we get? And you don't worry about the number value, you worry about the sign of it, okay? So that value right there is positive. So this is positive. I should say this. We're looking at the sign of f prime. And so this came out to be positive. When we put 3 pi over 2 into this, okay, so 3 pi divided by 2, it won't let you do fraction bars on this, okay? We get a negative value. And when we put 23 pi divided by 12, we get a positive value. Okay, so the derivative went from positive, okay, so that means the graph is going up to going down. We have a relative max right here, okay? And then it went from going down to going up. We have a relative min right here, okay? So the behavior of f is it's increasing, and then it's decreasing, and then it's increasing again, okay? So we would say, sorry, my papers were getting out of order, okay? We would say f of x is increasing on, and we wouldn't include 0. And here's why we wouldn't include 0. 0 is not part of the domain. So it'd be parenthesis 0 to 7 pi over 6. And then, I'm sorry, and I should have put a bracket on that, right? You probably were just saying that to yourself, right? So let me white out that. Okay, so 7 pi over 6 with a bracket, and then a union. You could also write and, okay? And then it starts up again at the 11 pi over 6 that we would include, because that's where it starts to increase, all right? And then to 2 pi. And once again, we wouldn't include 2 pi because it's not included in our domain at the very top. Okay, so it's not included up here, okay? I'm gonna zoom out a little bit so I don't have to slide it up as much, okay? And then we have f of x is decreasing on, and we would include 7 pi over 6 to 11 pi over 6 with a bracket, okay? And then the next thing we need to do is, because we have maxes and mins, or relative maxes and mins, we need to find f of 7 pi over 6. And what does that turn out to be? And we also need to find f of 11 pi over 6. And there's no other way to do this than with a calculator, because you don't have strictly a trig function here, okay? So this would be, I'm going to go back and I'm going to clear my function out, and I'm going to put in 1/2 times x and then minus cosine x. Okay? And then, because then all you have to do is go alpha, trace, and then number 1, and you're going to put in 7 pi over 6. And you get 2.699. Now you could also write this as 2.698, and that would be fine, okay? And then we're gonna do the same thing, but put in 11 pi over 6. And you get 2.014. Okay, so this one right here is a relative maximum, and this one right here is this one that you can't see that I'm pointing to so this one's a relative maximum and this one's a relative minimum, okay? So f of x, we'd say f of x has a relative maximum of 2.699 at x equals 7 pi over 6, because f prime of x changes from positive to negative. And if you stop there, you're wrong, okay? So positive, negative at x equals 7 pi over 6. Okay, it's incomplete if you don't add that, okay? You have to have that, all right? The next thing is f of x has a relative minimum of 2.014 at x equals 11 pi over 6, because f prime of x changes from negative to positive at x equals 11 pi over 6. All right, And so that's the end of the second example, okay? But you gotta make this statement, these two statements, to justify why you have a relative max and a relative min.